So our goal in this unit is to develop physically sound descriptions of the current in the linear regime of a MOSFET and in the saturation regime of a MOSFET. In the previous lecture, I discussed the general current equation that we are going to use. In this lecture, we'll discuss how that simplifies at low voltages, differences between the two contacts, and when there's a large voltage applied to contact 2. Then we'll be ready to apply this current equation to a nanoscale MOSFET. Okay, so we're going to take our general current equation, we're going to specify or simplify it for low drain to source voltage so that we can replace the traditional conventional expression with an expression that is more valid for a short channel MOSFET. And then we'll look at the saturation regime and discuss how this current equation simplifies so that we can replace the traditional velocity saturation expression with a more physical expression. Let's do low bias first. So here's our general expression. And remember, what the bias does is to change the location of the Fermi levels in the two contacts. So we have to work on F1 minus F2. So remember, F1 is very close to an equilibrium Fermi function. The assumption is that these are large reservoirs of electrons that are near thermal equilibrium. So F1 is a near equilibrium Fermi function with Fermi level EF1. F2 is also a near equilibrium Fermi function, but the Fermi level EF2 might be slightly different. We're going to apply a low bias and make it slightly different. Okay. So we will assume that EF2 is EF1 plus some small correction due to the applied bias that is applied to contact 2. Well, I could just subtract F2 minus F1, and I could divide by the difference in the Fermi levels of these two contacts, and I would have an approximation for the derivative of f of the equilibrium Fermi function with respect to the Fermi level. Now, if you look at the Fermi function, you can see that the only difference between energy and Fermi energy in that expression is a minus sign. So this is also an approximation for minus the F naught dE. That's the way I'm going to prefer to write it. So we conclude that F1 minus F2, which is our Fermi window, is approximately minus the F naught dE times the difference, the small difference in Fermi levels between these two contacts. Okay. All right. Under small bias, that difference in Fermi levels is very small. Now, why is there a difference in Fermi levels in the two contacts? Because we've applied a voltage to contact 2 with respect to contact 1, and we've pulled it down a little bit. So the rule is, EF, Fermi energy is an energy to the voltage minus the voltage lowers the Fermi energy by an amount minus Q sub V. Positive voltage pulls it down. So we conclude that under small voltage differences between the two contacts, F1 minus F2 is minus the derivative of the Fermi function with respect to energy times Q times the voltage difference between the two contacts. Okay, that's our approximation to the Fermi window under low applied bias. Well, let's take a look at that. The range of energies over which we're going to get a non-zero result then will be determined by this derivative. We know what the Fermi function looks like. It's constant below the Fermi energy. It's constant way above the Fermi energy. It only changes around the Fermi energy. If we take minus the derivative, you can see that we're going to get a peak centered at the Fermi energy. That's going to determine the energy dependence of our Fermi window. The width of that, well, it takes a few kT or several kT to make the transition from 1 to 0 in the Fermi function. So the width of that peak here is going to be a few kT. Now, if I call that my window function, that's something which selects out the energies over which current is going to flow. The window function is minus dF naught dE. and it has a width of a few kT, you can show, and I encourage you to try, that if you integrate that over all energies, the area under that curve is 1. So you can see that as we go to lower and lower temperatures, this is going to get to be sharper and sharper, but the area is always 1. It's going to behave as a delta function, which simplifies some calculations if we do those calculations at 0 Kelvin. All right, so now we can develop an expression for the current with a small applied voltage difference between the contacts. We simply use our approximation to the Fermi window. We said F1 minus F2 is proportional to voltage. That means the current is proportional to voltage. Well, we know that the current is proportional to voltage for a small voltage difference. That's just Ohm's law. Current is conductance times voltage, but now we have an expression for the conductance in terms of the parameters of the material that comprises the device. So, based on those steps then, we now have an expression. If we work out this expression, if we know the transmission, we know the number of channels, we can do this integral, and we can compute the conductance of this device. Well, before we do that in general, let's take a look at a simple specific case. Let's assume we have a ballistic device. The transmission is 1. Let's assume that we're in very low temperatures, so this Fermi window is very sharply peaked about the Fermi energy. We've just argued that it's going to behave as a delta function at the Fermi energy. That makes the integral easy. In fact, we can show then that the conductance is simply some fundamental constants times the number of channels at the Fermi energy. So that's a very simple result that happens at low temperatures. Now, if we have a very small nanostructure, then we can actually count these channels one at a time. So here's an illustration of an experiment that was done several years ago, done in the late 1980s when people first had the ability to be able to create these small nanostructures and do these experiments. We have a resistor here, a two-dimensional sheet with a high electron mobility. It's very short, much shorter than a mean free path if we do the measurements at low temperature. So we can assume that the transmission is 1. It's ballistic. And it has a very narrow width. In fact, not shown here, but this width is actually electrically controlled by 2 reverse bias Schottky barriers. So we can control the width. As it gets wider and wider, we would expect the conductance to increase. It's like parallel paths or conduction paths in parallel. But what we find when we do that is that the conductance doesn't increase just linearly. It increases stepwise. As soon as we've increased the width enough to accommodate 1 more channel, we get an increase in conductance of 2q squared over h. So those were beautiful experiments that showed for the first time that conductance is quantized into these discrete units of 2q squared over h. So this fact that conductance is quantized in small nanostructures is now a well-established experimental fact. When we make small electronic devices, if we make them small enough, we need to account for this quantization. Most of the time, we're going to be talking about much larger devices where we can simply take the number of channels as velocity times density of states, and we're not counting them individually. The device might be short, so we could be ballistic, but for most of our discussion, for all of our remaining discussion, we're going to assume that we have a large number of channels so that we won't have to deal with this discreteness of the number of channels. But you should be aware that it's there because sometimes it can become important. Okay, so what we would like to do is to calculate the current in a MOSFET in the linear regime. We have a general expression, current expression that we're going to take. And we've now seen that we can simplify that under low drain to source biases. This will be the expression that we will work out to determine what the current is in the linear regime of a MOSFET. Now, just as an aside, I'd like to talk about a large bulk device. By large bulk, I mean a device that would be very wide so that there are a large number of channels that I don't have to count them, and very long, many mean-free paths long, so that I will be in the diffusive limit. This would be the kind of sample that we might do a measurement on. We might do a measurement of the conductance, and you can recall that we would often equate the conductance to the sheet conductance in ohms per square times the width divided by the length. So the wider it is, the higher the conductance, the longer it is, the less the conductance. And the quantity that characterizes this two-dimensional material is the sheet conductance. If width equals length, I have 1 square, and the conductance is the sheet conductance. Okay. So I could solve that equation for the sheet conductance and relate it to the conductance. Remember now, we have an expression for the conductance from our current expression, so we can work out the conductance. And then if we know the length and the width, we can determine the sheet conductance. Okay. Now, you may also recall from basic semiconductor physics that we often write conductivity as NQ mu, or sheet conductance as the number of electrons per square centimeter times the charge on an electron times the mobility. So that's a common way to write the sheet conductance. All right, so how can we use this information? We have an expression for the conductance of an arbitrary material in terms of its transmission and number of channels. And we have an expression for the sheet conductance. Given the conductance of a device, of a large device, we can deduce what the sheet conductance is. So if we just equate those two, we'll get an expression for the sheet conductance that we can work out. Okay. Let's work it out assuming we have a very long device, many mean-free paths long. So the transmission will be very small, mean-free path divided by length. And we now have an expression for the sheet conductance that we can simply work out and determine what the answer is. All right, I won't go through all of the math. I can point you to a reference where you can find that, but here's our expression for sheet conductance we just developed. You also recall that we can compute the electron density per square centimeter by integrating the density of states times the probability that the state is occupied. That's the Fermi function, and we can do that integral. We know what the number of channels is. We can make a simplifying assumption that the mean-free path is independent of energy, or it's some average mean-free path, and pull it out of the integral. And then we can do the integral. If you do those integrals, this is the answer that you will get. So you might want to try working out those integrals. We get an expression for the sheet conductance, and we get an expression for the electron density per square centimeter. You can see both of them involve this exponential because I'm assuming non-degenerate conditions. Both of them involve an exponential e to the Fermi level minus bottom of the conduction band over kT. Well, where are we going with this? We can take that expression that we just worked out and we can equate it to sheet carrier concentration times charge on an electron times mobility. And then we can deduce what the mobility in this sample is. Okay? If you do that, this is the expression that you will find for the mobility. V sub t, a velocity, times the mean free path for backscattering divided by 2 kT over q. V sub t, we will discuss several times as we proceed because this will be a velocity that is important for us in our subsequent discussion of ballistic MOSFETs and MOSFETs in the presence of scattering. So V sub t is termed the unidirectional thermal velocity. In equilibrium, the average velocity is 0, but this is the velocity, this is the average velocity of the half of those electrons that have a positive x-directed velocity, assuming we're non-degenerate. So that's a thermal velocity. It's about 10 to the 7th centimeters per second for electrons in silicon. Now we also know, since we're assuming that we're near equilibrium, small voltage is applied, that d over mu is kT over q. That's the Einstein relation. So we have the mobility we can deduce the diffusion coefficient, and that argument will give us a very simple expression for the diffusion coefficient. Thermal velocity, unidirectional thermal velocity, times mean free path divided by 2. So we have a simple expression for the diffusion coefficient. This is an important expression you should try to remember, because this allows us to deduce what the mean free path is, and the mean free path is important because it tells us what the transmission is through this device. So it's important, and it's easy to remember, and it's something that we will make use of. Diffusion coefficient is thermal velocity times mean free path divided by 2. So the mobility is easy to measure. We'll usually be able to find out what the measured mobility is. We can convert it to the diffusion coefficient with Einstein's relation, and then we can deduce what the mean free path for backscattering is. That's how we'll use this expression. Okay, we'll do that later. But let's look at the saturation current now. If we apply a large voltage difference between the drain and the source, we can develop an expression for the saturation current, which will be more physical in general than our conventional expression that has this velocity saturation in it. Okay, so we need to go back to our current expression, and we need to simplify it for a large voltage applied to contact 2, which will represent our drain. Well, remember, the Fermi function of contact 1 is an equilibrium Fermi function with Fermi level EF1. Fermi level EF2 has been pulled down by the large voltage applied to the drain, the second contact, so it's been pulled down a long ways. And what that means is that F2 is about 0 for all energies of interest to us, because we've pulled the Fermi level so low that the probability of any state in the conduction band, if this is an N-channel MOSFET, the probability of it being occupied is essentially 0. Okay. That gives us a very simple picture for how current flows when a large voltage is applied to contact 2. So we have our Fermi level in contact 1. Our Fermi level in contact 2 has been pulled way down. So now our Fermi window is a very large range of energies. All of the energies in the conduction band below Fermi level EF1, all of those can contribute to current flow. If there's an empty state there, contact 1 will try to fill it, and then it will flow out into contact 2. But there are empty states everywhere that can be filled by contact 1 and then emptied by contact 2. So we get much more current under high drain voltages because all of those states contribute to the current flow, because now we have a very large Fermi window. Notice also that if I keep increasing the voltage, it won't give me any more current because there are no more states to fill and empty. So the current will have saturated. That, in fact, is how current will saturate in our nanoscale ballistic MOSFETs. Now remember, at low bias, we had a very small difference in Fermi levels. We had a very small range of energies that contributed to current flow, and we could increase that range of energies by increasing the voltage. Current is proportional to voltage under small voltages, but current is independent of voltage when the voltage is large enough. So small Fermi windows under low drain to source bias, large width and energy of Fermi windows under large drain to source biases. Okay. Under low bias, the current flows near the Fermi level, which are almost the same in both contacts. Under high drain bias, the current flows underneath the Fermi level of the first contact. So we can summarize. We've taken our current expression and we have simplified it for low voltage difference between the two contacts, and we've simplified it when we apply a large voltage to contact 2. These are the expressions which we are now ready to apply to MOSFETs to get the linear region current and the saturation region current. So that'll be the topic of our next lecture, but we'll simplify things a little bit in the next lecture by, first of all, assuming a ballistic MOSFET. So we'll assume that the transmission is 1, and we will try to understand the IV characteristics of a ballistic MOSFET. Now, there's one thing that we have to do. Somehow we have to get MOS electrostatics into this discussion. And we know that MOS electrostatics is very important. There is a gate that induces a charge, minus Cox, Vg minus Vt, and we have to account for that in our calculations. Well, we will discuss that in the next lecture.